Hello, today we'll discuss multi-rate digital signal processing. From that, we'll discuss the downsampling and upsampling. Which is also called as a decimeter. So downsampling of the signal, downsampling, this is the process. Downsampling is the process of decimating a signal x of n by an integer factor m, and this can be represented by the block diagram like this. This is your input x of n, this is the output y of n, and this is the decimeter factor m, and it is shown by the arrow downward. Downward means it is a downsampling, and therefore y of n is equal to x into m of n. This m is the integer factor, or this is also called as the decimeter factor. So the sampling rate compressor is represented by this down arrow along with this decimeter factor m, and therefore this m is called the decimeter factor. And therefore this is the output. Hence the sampling reduction, we have to reduce the sampling. Therefore the sampling rate reduction is achieved by discarding, removing, we can call it as a removing, discarding m minus 1 samples for every m samples, for every m samples. And now we'll see one signal which is a downsampling for m is equal to 3. So the signal is given, suppose like this. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is a 1, 2, 3. This is a 1, 2, 3. This is a 1, 2, 3. So this is your input x of n, and this is n. Okay. So therefore we have to downsampling this function for m is equal to 3. When you downsample this for m is equal to 3, therefore we have to discard or remove m minus 1 sample. So it is a 3 minus 1 is equal to 2. So we have to discard 2 samples for every m samples. So we will discard these 2 samples, 1 and 2. We will keep the sample. We will again discard these 2 samples, 5 and 6. We will again keep these samples. So in this way, we have to discard the samples for every m samples. So the output will become now, this is again 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and this is 11. So now this is your input x of n, and therefore we have to find the output now. So the output we can find here, that is y of n is equal to x of 3n. 3n means here m is equal to 3. So we are removing this 3 minus 1, that is 2 samples. So this is 1, 2, and we are keeping this sample. Again 1, 2, we are keeping this sample. 1, 2, we are keeping this sample. Okay. So the output will now become, this is y of n is equal to x of 3n. So this is your 1, 2, and 3. Okay, so 3 samples are there remain. Okay, actually this is 1, 2, 3, 1, 2, 3. This is 1, 2, 3, 1, 2, 3. So if you remove these 2 samples, then we have only 3 remain with us. Therefore, output is here, this. So this is a downsampling signal for downsampling signal for m is equal to 3. Okay. Now upsampling, which is also called as interpolator. Interpolator. So we have seen that upscaling is the process of increasing the sampling frequency. This is the process of increasing the sampling frequency of the signal. And the upsampling is also called sample rate expander. Upscaling, this is called, upscaling is called the sample rate expander. Sample rate expander, or it is also called as interpolator. Interpolator. Okay. So the interpolator is represented by the upward arrow. Interpolator is represented by the upward arrow like this. So this is your input x of n, the output y of n, and this is represented by the interpolator is represented by the upward arrow. Okay, with the interpolation factor L. This L is called as the interpolation factor. L is called as the interpolation factor. So this output will be here x of n by L. Okay, so this is the block diagram of append arms. This is the block diagram of an upsampler. This is the block diagram of an upsampler. Okay, the interpolation factor is L. So we'll discuss the upscaling of x of n for L is equal to 4. We'll discuss the upscaling of the input function for L is equal to 4. The input function is given, suppose, like this. So this is y of n is equal to x, x of n by L. So n is here, n is here, sorry, L is here 4. L is 4, and therefore for upsampling for each sample of x of n, the interpolator factor includes L minus 1 zeros. Therefore, the signal is given like this. It is 1, this is 2, this is 3. So this is your output function, which is equal to y of x of n by L. So here we are taking here L is equal to 4. Therefore, we have to upsample this given signal. So when you upsample, for upsampling, for each sample, of x of n, the interpolator includes L minus 1 0 values, n minus sorry L minus 1 0 values samples to form a new signal. So we have to include L minus 1 0 value samples to form the new signal. Now here L is equal to 4. Therefore 4 minus 1 is equal to 3. So we have to include 3 zeros samples between the signals to give the new signals. So we have seen that here we have to, this is your output signal, and therefore we have to find the input signal. How we have to add the 3 zeros. So we will put like this 1 2 3. So your input signal will become, to form the new signal, the input signal will become here like this. So this is x of n, and here we have got here 4 2. So we have to add 1 2, 3, and this is a 4. So it is a 2. So we have to, as L is equal to 4, so we have to add the 3 samples. So in between these we have add 1, 2, 3. Similarly here 1, 2, 3. Similarly here 1, 2, 3. Because we have to add the 3 samples between the given samples. So here we have added the 3 samples. Then we have to add the 3 samples on this side. Now it is here 2 is having the negative sign, therefore we can have the 3. This is 1, this is 2, this is 3, and this is minus 2. Again we have the 2, it is positive at 3. Again we have the 3 samples here. This is 1, this is 2, this is 3, and this is 2. So in this way we have upsample the discrete time signal for the interpolation factor n is L is equal to 4. So this is the figure, that is a upsample discrete time signal for L is equal to 4. So in this way we can upsample or downsample the given signal. Thanks for watching the video.